Hi, everybody, and welcome to our webinar. My name is Karina Barbosa, and I'm here with Glenn Sharrock and Jim Hazard. We are excited to be presenting this section on behalf of our ITASCA consulting team. While ITASCA has offices in 8 countries, today we are joining you from Australia, where our team mainly works in the geotechnical and hydrogeological fields. In this webinar, we'll briefly discuss our work and present a couple of interesting models, including an example of an open stope model with zone joints. Let's get started. Thank you once again for taking the time to be here. We appreciate your interest and your time. If you are attending this webinar, it's likely you're into mining, as well as involved in analytical and numerical models. And we find this very exciting because mining is a field that's in high demand, especially now that we seem to be living the electrification boom. In very simple terms, as ore grades decline and mines become deeper, we are increasingly face a more complex rock mass and high stress concentrations, which in turn lead to more difficult geotechnical and hydrogeological issues, such as seismicity, cavability, stability, or groundwater. Important to keep in mind that every model is an attempt to represent reality. The model certainly contains simplification and assumptions given the heterogeneous nature of the rock and its surrounding. Still, these numerical models can be extremely complex. Depending on our area of interest, we may seek an understanding of rock breakage at the grain size as an assembly of minerals, or we might focus on large volumes as the rock mass. That's why, depending on the model application, ITASCA offers a range of software options to meet the needs. And these are the ITASCA commercial software, as you see listed here, and they can be used to model different conditions and problems. As consultants, we use our ITASCA software on a daily basis in our projects, and we can also use other softwares and tools, and we can perform empirical analysis. The empirical analyses are often conducted in parallel with numerical modeling, using numerical inputs to broaden the scope of the assessment. While ITASCA has a range of robust and mature software, we continuously improve them to incorporate more data and information that comes with new technologies and advances in the mining sector, enabling them to run faster and produce reliable results. The IMAT, which stands for ITASCA's Mining Analysis Toolbox, is our most recent release, and it is a modeling pre-post processor powered by FLAC3D. IMAT is suitable for mine-scale open pit, underground, and caving projects. It is extremely user-friendly, and it completely eliminates the need for scripting. IMAT automatically compiles fish codes for the user. The IMAT allows tracking the mine sequence and provides a clear workflow to build, solve models, and analyze results. And IMAT also extends beyond a numerical modeling software, as it caters for multiple field data sources, including seismic data, block model borehole, and other monitoring data. The goal is to incorporate all of these data sources to improve our numerical models. If you want to know more about our software, please check it out on our website and get in touch with us. And over the years, ITASCA's engineers and software developers have a proven track record of innovation working alongside our ITASCA consultants. We have developed new strategies, tools, and methodologies to better understand complex and very large models. While the computational limitations are less critical now than they were a few years ago, most of our models are still very computationally intensive. And today, ITASCA can run large and complex models using MPI and cloud computing. And these large and complex models require the combined expertise and experience of our team to post-process and analyze the results. It is truly amazing how changes in hardware and software are evolving fast, and we can now look at the interaction of excavations taking into account the entire mining footprint. So whether the challenge is an open pit or underground, whether it's a project or an ongoing operation, our ITASCA Consulting has a multidisciplinary team to provide practical field solutions to design issues and mitigate risks. In our work, we are specialized in the application of ITASCA's modeling tools to solve difficult or unusual problems across a wide range of mining methods and materials. The design of footprint is also changing, and we now have these extremely large layouts such as caves or super caves. So we see changes in design, equipment, and monitoring data, along with opportunity for real-time optimization. And as we spoke about large and complex models, we want to share some insights from data collection. We want to highlight that ITASCA has in-house expertise to design field data collection campaigns, conduct the geotechnical characterization, compile and validate data. It's also great when a mine site can collect large amount of data, but it's also important to distinguish between different levels of confidence. We can work with the people on site, and these allow us to evaluate the quality of the collected data and its variability, and understand the level of confidence in the geological, geotechnical, and hydrogeological information input into the models. Overall, we are seeing more projects being developed in variety and complex environments, often covering large footprints. And we know that these environments might be outside of our existing experience. And we are here to offer our knowledge in data collection, processing, and running a variety of models and dealing with complex fields. And we are bringing this up because the outcome of a model can change significantly depending on the input parameters. For example, the structural geology, such as faults and joints, are equally important in determining the stability of an open pit and a stope located deep underground, as both cases tend to be structurally controlled. Understanding rock mass parameters and how to transfer them to analytical and numerical models is essential. Numerical models of different scenarios and sensitivity studies can be built to account for variation in structural geology, based on the level of confidence of these structures. These allow us to rank design options according to geotechnical risks, and it is a reliable way to assess mine designs. In this webinar, we'll be talking about stability within the context of numerical modeling. ITASCA's portfolio of completed models is extensive, and while we would love to showcase some of our large and complex models, confidentiality agreement restricted our ability to do it. So today we will present some interesting examples of high-stress environment to demonstrate the rock mass responses when tunnels and stopes are excavated. As we are more likely to be working in deep or even ultra-deep mines, we want to be able to more rigorously represent the ground conditions so we can capture high deformations. Basically, we want to know if the excavations are stable, or if we are having squeezing or crunching, or what kind of support needs to be installed, as these are some of the important things impacting stability. As it is illustrated in these pictures, we see that the size and the shape of the rock blocks formed around a tunnel and the failure process are conditional to structural geology, such as joints, faults, and the proximity and location of surrounding excavations, as well as the local induced stress states. And when running three-dimensional numerical models, we first select the software. And here we will discuss these two options, which are FLAC3D and 3DEC. FLAC3D is an explicit finite difference software to model the behavior of materials that are subject to plastic yielding. FLAC3D is a continuum-based code, but it can also incorporate structures into the model, either implicitly using the ubiquitous joints or as discrete structures using interfaces or zone joints. The 3DEC is a hybrid continuum discrete element software for model block or highly jointed systems. Materials are represented by a network of continuous blocks with surface conditions, and these blocks may rotate or slide along joints, and the joints can also open or close. Blocks can be rigid or deformable, and 3DEC is capable of simulating large displacements. Actually, FLAC3D is best suited for modeling rock masses that behave predominantly as continuous median with limited jointing, while 3DEC is more appropriated when the mechanical behavior is strongly influenced by joints, faults, or the structural discontinuities. While we can build interface in FLAC3D, and we have been doing that, it can be a bit tedious, and it can take time when we have hundreds of these structures, and if they have some complex geometries, as you see in this picture. But these structures can now be simulated in FLAC3D using the zone joint, since the zone joint logic was introduced as an alternative to interfaces and is simpler to build. The advantage of zone joint is that they are two-sided, so the order in which they are created do not affect the results, and force and displacements at the intersections are more accurate. Both zone joints and interface logic can apply a linear Coulomb shear strength criteria, and we will have failure intention once the tensile strength is exceeded. For the constitutive models, both FLAC3D and 3DEC have the option to use IMASS as a built-in constitutive model. IMASS stands for ITASCA Constitutive Model for Advanced Strain Softening. One of the key aspects of the IMASS is the ability to capture the post-peak behavior of a rock mass, in particular the progressive failure and disintegration of the rock in the post-peak, as we see in this schematic illustration. The graphic is showing that there is a bilinear envelope in the post-peak from point A to B and point B to C, which captures the two-stage softening behavior of a rock mass being excavated or undergoing caving, including the bulking in the material and the change in the modulus of the material. IMASS is based on empirical relationships and uses strain and zone size dependent properties. This constitutive model is used across several projects at ITASCA, and it has been used in the examples that we will show here. This is an example of a back analysis for the drifts at Westwood Mine. We can see the similarity between the photo and the schematic illustration below. We have a very anisotropic rock mass in high stress concentration, which has been deformed quite a lot. And on the right-hand side, we have a model built in 3DEC by ITASCA, so please feel free to check out the publication for more details. The objectives of the back analysis were to better understand the mechanisms controlling rock mass performance and to obtain a calibrated model for predictive stoping simulations. The calibration uses properties derived from field and laboratory, and we have illustrated the boundaries of the initial excavation here, and we are plotting the amount of horizontal displacement recorded in the model. One of the benefits of this model is to have a more accurate representation of the depth of damage and the mechanism that arise near the drift. As mentioned, 3DEC is really good at modeling block and highly jointed systems, so we can capture these large displacements in the drift. We see the anisotropic rock mass, the breakage of blocks, and the hinge lines formed, as well as the confinement that occurs when buckling around the excavation. Now we have 3DEC models with ground support. These examples illustrate the bonded block model, BBM approach, which can be used to simulate the rock mass as bonded polyhedral elements. So these blocks can break along the subcontacts or bonds due to stress concentration. And we have a hybrid boat model to represent the ground support. The example on the left-hand side can be found on our website, and it shows the emergent fragmentation around a mine drift that occurred as a result of a stope excavated nearby. The model mimics the initiation of crack, coalescence, and propagation, which fractured the rock mass. And in this model, the minimum principal stress reaches up to 90 MPa. On the right-hand side, there is a numerical model to study the performance of tunneling at depth under a cave-induced stress path. This is also a publication from ITASCA. Essentially, the movie shows the transient loading on the ground support installed in highly stressed fractured rock. In this case, we can observe how the effect of debonding cables and bolt installation timing influences the bulking evolution around the excavation. The effect of the damage to the cables themselves is also investigated. The hybrid bolt model in 3DEC allows for visualization of the damage developed around the tunnel and the breakage of some of the support elements. The outcome is that intense axial straining can be mitigated through debonding, and intense shearing can be reduced through the use of bolts with higher shear resistance, such as rebars. Moving on to FLAC3D, we have two examples of tunnel stability where ubiquitous joints are used to represent the foliation in these models. The orientation of the pre-mining situ stress relative to foliation, the abatement, and the alignment of pillars significantly influence the damage of these excavations, and this has been simulated in some of our large parametric studies. So we observe this issue regarding the orientation of the tunnels, whether the footprint should be oriented relative to these structures to promote caveability and also to ensure stability of the excavations. Additionally, it's equally important to understand the in-situ stress, which we define as the trend of the major principal stress, the dip and the gradient, and how these factors affect stability. And without further ado, we will show our example of stope stability in detail. We picked a relatively simple model of a high-grade copper ore located deep underground. The stope geometry is from a real case operation where the mining method is sublevel long hole open stoping with cemented backfill. The goal is to run a stability analysis for the extraction of these large open stopes in a complex geological environment. Following up on the previous slides, we have used the IMASS for the constitutive model of the rock, zone joints for the structures, and ground support with cable bolts as we simulate stability in FLAC3D version 9.5. The figure on the right-hand side illustrates our stope excavated about 1,500 meters below the surface. And in this scenario, the stope is situated within a block rock mass intersected by dense structural features, particularly in the hang wall, which pose significant challenge to ground support performance. We will show how we can capture both structural and stress overbreak, as well as the impact of supporting controlling overbreak. So let's start. First, we need to create a deformable ozone model in FLAC3D. For that, we started by preparing our model geometry, which can be created or imported into a CAD software. We need to represent the tunnels, our large stope, the ground support, the geotechnical domains, and the joints. In our work, we used the Rhinoceros 3D, which allow us to plug in our Griddle. Griddle is a fully interactive and general-purpose mesh generation developed by ITASCA. Since we are building a fully conforming mesh for this model, the commands intersect, remesh surface, and volume mesh in Griddle were extremely useful for creating this geometry. The figure on the left-hand side shows the mesh and the sequence for the model created with Griddle and imported into FLAC3D. These are the dimensions of our stope. The height is about 170 meters. The stope is 27 meters wide and 40 meters in length along the strike. The extraction sequence has 5 stages, which started with tunneling and installation of ground support using cable bolts. And next, we extracted the throw undercut, then create a 5-meter slot, followed by a 10 meters ring firing 1 and a 15 meters ring firing 2, as illustrated here. These pictures are not on scale, as the right-hand side shows the isometric view of the regional extent of the model in FLAC3D. The model boundaries are positionally far enough and further away from the excavations to ensure that they do not affect the behavior in the area of interest. Note that we represent the original topography here, and in the case of a more complex model, we could have an open pit, the access infrastructure, and other stopes to represent all the excavations in the underground. The model has different geotechnical domains represented as a series of DXF wireframes, which are also imported into FLAC3D. This cross-section shows the area of interest, with our stope located about 1,500 meters below the surface. Overall, the rock is quite competent, but we also have some thin domains that we refer to as faults in this example, and some of them can gradually reduce the rock strength. And for this model, the zone joints are used as an alternative to interfaces. The zone joints can be used to better represent multiple intersecting joints, faults, or discontinuities in small strain in FLAC3D models. And the more coulomb is the default joint behavior. We have simulated two models, which we named Model A and Model B. We have an identical geometry for the stope, the domains, and the in-situ stress. The only difference between the two models is the number of zone joints located parallel to the hanging wall. The Model A includes 147 zone joints in total. The structures parallel to hang wall have slightly lower strength parameters compared to those perpendicular to the hang wall, as well as those random located around the stope. And Model B includes 90 zone joints. Essentially, we have reduced the number of structures parallel to the hang wall, and all structures have the same strength properties as those perpendicular to the hang wall in Model A. The zone joints for Model A and Model B are illustrated here, and our goal is to capture the influence of these structures parallel to the hang wall. In the following slides, we will present the results for Model A and Model B side by side for comparison. And here we plot the results in a cross-section placed near the middle of the stope once the excavation is completed. So let's start with the major principal stress component, sigma 1, which is steeply plunging towards the north near vertical. And under these stress conditions, when we look around the drives and the stope, we see that the stress increases above and below the excavation as sigma 1 is nearly vertical. And if you look at Model B, it shows a large stable span. When the horizontal confinement sigma 3 is low, there's a stress relaxation behind the hang wall of the excavation, which contributes to the hang wall to remain stable. And if you look back at Model A, it shows that overbreak and instability are structurally controlled since sigma 1 is nearly vertical. Instability will mainly follow the discontinuities or weak planes, and it's not stress-driven failure. Since Model A has a number of zone joints parallel to the hang wall, they may continue to fail until competent rock is reached. And these are the state by average plots used to identify any small amount of shear and tension in the models now. So the past state is excluded. We should highlight that the state by average plot does not necessarily represent failure. And Model A is showing that the hang wall is under tension, which means that the bulk material adjacent to the joints in the hang wall is experiencing tensile normal stress. So the rock mass might be pulling apart. Now the joint slip plot shows the slip magnitude, which is the relative shear displacement between the two sides of the joint. And the Model A is showing a moderate movement in the hang wall and partial activation of some joints, which may ultimately result in full detachment, since we have a case of a large open stope. However, Model B shows very little slip magnitude and no reactivation or detachment is expected. Here are the videos of major principal stress, state by average, and joint slip for Model A, which are played together to illustrate the model's progression through the excavation stages. We use the videos in our consultants to provide a clear visualization of the model's behavior, and it would be good to include other cross-sections as well. Now we plot the results of the velocity magnitude in the stope wall rather than a cross-section, and the velocity magnitude is a metric that we use in our projects. and it provides a very good indication of areas of the model that are actively failing. For the FLAC3D analysis reported here, the Stope is considered to be in a state of failure when the numerical velocities exceed 1e-5 meter per model step. And this plot shows that overbreak and instability occur in the hang wall of model A, but not model B. Also, the axial forces in the cable bolts are represented here. The red pattern indicates the locations where the axial capacity of the cables has been exceeded. And if you look at the velocity magnitude plot in the cross section, it can give us an estimation of the depth of breakage, which is also consistent with our previous plots. And here we have put all these plots together so we can compare model A and model B. And in the next slide, we will have a close look at the hang wall. And we have already presented these plots, but we want to emphasize the influence of the zone joints because the zone joints are a critical component for these models. We can see that overbreak and instability of the hang wall are structurally controlled. By simply decreasing the number of structures in the hang wall, we shifted from unstable to stable stope, from experience some movement along the joints or none, also failure of the rock mass or not, as well as cables failing or not. And in this webinar, we discussed that by definition, every model is an attempt to represent reality. And the numerical models will include simplifications and assumptions, but they can help us to understand complex geotechnical behavior. And ITASCA has different software that allow us to address specific challenges. And through continuous advances in software, data integration, and computational power, we can achieve more realistic and predictive behavior. We can run and analyze large and complex models, and while the quality data and local understanding of the rock behavior are critical for the model's outcome, it's also important to update the models. We saw some examples of models, including the zone joint in FLAC3D, and similar to open pit, the stability of stopes is structurally controlled. So the numerical modeling can be used to select a safer design, to improve decision making and reduce uncertainty in mining projects. And since we are providing an example of an open stope, we compiled a list of projects and research conducted on this topic across ITASCA to demonstrate our capability. And last, these are the references that appear in the slides, including the ITASCA publications that I mentioned. And thank you very much for listening.
This is Jim Hazard. I will now dig into the details of how to model faults and discontinuities in FLAC3D and IMAT. So it is certainly possible to model discontinuities in FLAC3D, even though you may think of FLAC3D as a continuum modeling program. It is possible to model discontinuities, and there are different ways that we do that. There's really two main ways of doing this. Number one is using the ubiquitous joint constitutive model. So you can see here on the left, I have a little conceptual picture of what that might look like. Imagine you have a set of parallel, closely spaced joints. You don't necessarily want to put all of those joints in your model as actual discontinuities. You can assign the ubiquitous joint constitutive model, and the continuum will then behave as if there were a set of parallel joints in there. You specify an orientation and a strength for those joints, And again, the continuum will behave as if the joints were there, but we're not actually putting discontinuities in there. If the movement, for example, separation and shearing on actual discontinuities is important, then you probably want to explicitly put specific discontinuities in the model, especially if you have major faults or other things that have been mapped, and the behavior of those things is important, then it is possible and advisable to put them in as discrete structures within the model. Now, interfaces and zone joints. So these are two very similar things, but there are some subtle differences here. Before FLAC3D version 9, we only had the ability to put in what we call interfaces. These are true discontinuities. So the way that it works is that you identify the faces where you want to have a fault or a joint. You do a separation, right? So you're duplicating the grid points. And this allows there to be movement between the two sides, right? Opening and potentially shearing. But the way that the interfaces work is that they're really one-sided. So what this means is imagine you're sort of painting on this sort of discontinuity onto one side of this split. This is shown in purple here, and on the other side, it doesn't consider itself part of the discontinuity. So all of the calculations, the forces and displacements and so on are calculated on this purple side, and the gray side here is just reacting. This is fine. This works okay. We've done it for years. It just gets a little bit weird when you start considering complicated intersections. Because these are one-sided, what is actually happening at these intersections, and which side is the dominant one and which side is not, and so on. Post version 9, we have a new technology which we call zone joints. And what this is it's a true two-sided discontinuity. So again, you identify the faces where you want to slip to occur or separation. You can do a separation, you're duplicating the grid points, same as before. But now what we have is a two-sided joint, so we don't have to identify which side is the interface is on. Both sides will interact with each other when they come into contact, and you get a slightly more realistic behavior. And it also makes the joint intersection behaviors and calculations much more accurate. So post version 9, I would say probably more people are using this zone joint technology and moving away from this older interface technology. Either way, if you're using zone joints or interfaces, or in fact, ubiquitous joints, we assume a Coulomb shear strength criterion. So this is probably familiar to you. The shear strength is dictated by a user-specified cohesion, a user-specified friction angle, and then the normal stress and potentially water pressure. So if you plot, for example, shear stress versus shear displacement, you will see a linear behavior as the shear stress increases according to some user-defined stiffness. Then you reach the shear strength, which is the cohesion plus the normal stress times the tangent of the friction angle, and then this thing will start to slide, right? It is possible to specify a residual cohesion and a residual friction angle, which is different from the peak. And then what that means is that once sliding starts, the joint actually weakens. Okay, so the strength decreases instantaneously, and you will see a new strength, and it will continue to displace in shear at a constant shear stress, and it will just happily slide along there. If I plot instead shear strength versus normal stress, you can see the typical, more Coulomb curve that you're all used to seeing, where at zero normal stress, you have a strength that's determined by the cohesion, and then the strength increases according to the friction angle. And then again, if this strength is exceeded and the thing starts to slide, you can drop down to this residual strength. And often people will set the residual cohesion to be 0, which sort of makes intuitive sense. And often people will set the residual friction angle to be the same as the peak friction angle. So you might see the residual strength curve looks like this. There's also a relation for tensile strength. So you can specify a non-zero tensile strength. And again, it will just open up, and the normal force will increase according to some user-specified normal stiffness until that tensile strength is exceeded, and then it essentially breaks, and the normal force goes to 0 by default. Okay, so how do you put the discontinuities into FLAC3D? For ubiquitous joints, it's easy. You just specify an orientation and a strength, a cohesion and a friction, and you just assign that to zones. You don't need to worry about changing the geometries around or anything like that. You just identify a region that's full of ubiquitous joints, and you assign the necessary properties, and it will behave as if there were a parallel joint set there. For the zone joints or the interfaces, it's a little bit more complicated because you need to identify where these discrete features actually are. And so the way it works is you need to identify a set of faces, a set of zone faces, and then you can do a separation operation where the faces are separated and the grid points are duplicated. And again, this allows there to be relative movement between the two sides. For complicated geometries, if you have a bunch of intersecting faults, maybe like in this example here, you will almost certainly need to use Griddle or some other similar software to generate the geometries such that the faces line up with the actual mapped discontinuities. It is also possible to simulate discontinuities in IMAT. Again, you could use ubiquitous joint model. There's no built-in way to actually create true interfaces. Again, you could potentially use Griddle, and I'll show that on the next slide. But one thing you can do within IMAT without leaving the program is create these weak zones. So as you may or may not know, IMAT builds the models using an octree system. And what this means is that, the whole model is composed of little cubes, and you have small cubes in the region of interest, and you have bigger cubes away from the region of interest. And so you can see here, for example, we have an open pit. It does a pretty good job of matching the geometry of this open pit, but it's not perfect. It's not an exact match. And so for modeling a discontinuity or a fault, it's not that easy to have an exact match to the surface of this fault. So what we can do instead is just find all of the zones that are maybe touching this fault or within some distance of the fault and give them a set of weak properties, right? So instead of modeling a true discontinuity, we're just modeling a weak zone here. In some cases, that's great. In some cases, maybe that's not great. If modeling the actual discontinuity itself is important, it's still possible to do this within IMAT, but you just need to generate the geometry first with Griddle. So if you generate the geometry and you have identified faces that line up with certain faults or joints, you can import that into IMAT, and then everything becomes relatively easy, right? You can choose the faults, and then you can assign properties to them, using the IMAT interface. So here I've got a model with just one fault in it, and I can specify friction angle and cohesion and tension limit and so on. Once I've set up my model and properties and so on, I hit run, and the operation of separating and duplicating grid points and assigning properties and all that stuff just happens automatically. And then when it's done calculating, I'm back in IMAT, and I can look at the results within IMAT. So here's the same example. Now I'm just looking at the shear displacement on the fault. Of course, there are other things I can do here, cut planes and isosurfaces and so on. This is just showing you how it's possible to look at results on these discontinuities within IMAT. So that's basically it. To summarize, if you want to model discontinuities in FLAC3D or IMAT, you can use ubiquitous joint model. You can use interfaces or zone joints. These are very similar. You could also just make a band of weak zones, and that's relatively easy as well. Whichever method you use, we will be assuming a Coulomb shear strength criterion where you specify a cohesion and a friction and possibly a tension strength. If you have relatively simple geometry, like something bedded, maybe a coal mine, it would be possible to just build this in FLAC3D and identify the faces that form the beds and do the separation and so on. If you have more complicated geometries with intersecting faults, most hard rock mines, you would need to create the geometry in Griddle or similar, and then import that into FLAC3D or IMAT. And that's all I have. Thank you for your time.
Great. Well, thank you very much to all our presenters. We have Karina and Glenn online. If anyone has any questions about the presentation or anything that you've seen today, please enter the questions into the Q&A tool, or feel free to use the chat also. I put a note in the chat if anyone's interested in a free 2-week trial of any ITASCA software. We have a link in there to set up a discovery call, meet with us, and that we can send you some information about how to get a free trial for 2 weeks. Also in the chat, if the recording of the video of today's webinar will be available on ITASCA Software's YouTube channel tomorrow. So feel free to check that out. A link to the video will be sent out to everyone who's registered for the webinar. So expect an email with a link to that. Okay, so are there any questions? Karina or Glenn, would you like to add anything?
The only thing I'd like to add is really just to enhance what Karina said. The software's come a long way. Computing hardware's improved a lot. For those people that are looking at that are currently using the interface logic, the zone joint logic is really so much better. It's more robust. There's no doubt about it. It's more it's quicker. It's significantly quicker for doing things like face separation and actually initializing joints in the model. So it really is a lot better. So I really just wanted to make that comment.
Great, thank you very much, Glenn. There is a question. I haven't experimented much with zone joints yet, but when generating the planes with Rhino Griddle, do they need to form part of a closed watertight volume, or can they be floating within the closed volumes? So yes, you can have essentially imagine you have a box representing the model domain. You could have a circular joint in the middle of that box, maybe at tip and dip direction 45 degrees. And when you go through the meshing process using Griddle and do the 3D volume meshing, it's essentially going to identify the faces of the zones that fall along that circular disc. So yes, it is possible to have a free-floating joint. What FLAC3D will look for in the FLAC3D grid file, or again, you could export that as a 3-deck model. There's a little bit of difference there, but let's say we're talking FLAC3D. Essentially, it will identify those as internal faces compared to like external boundary faces. And based on that, you'd be able to essentially create a group representing the faces on that disk, and then assign those to zone joints, and then assign properties or constitutive model. A little different in 3-deck, because in 3-deck, of course, you have to have a through-going cut of any block. So if you started with a single large block representing the model domain, you would put a complete cut through that block, and then you could go back and create a range based on that disk that falls on that cut and you would just assign joint properties to the region that represents the disk, and then intact rock properties outside of that. It actually becomes a little bit easier to do that for FLAC3D in that sense. And then IMAT can import a FLAC3D grid. It'll look for those internal faces. You can select the ones that represent a fault as opposed to maybe some kind of lithology separation. And then within the IMAT dialog, you can go in and assign material properties. So thanks for the question. Let's see, how do you incorporate modeling of backfill material reactions with zone joint modeling in hard rock type? Let's see, let's try that again. How do you incorporate modeling of backfill material reactions with zone joints modeling at hard rock type? I'm not sure what the word Prutos is, responses. Whereas the fill behaves with high plasticity. Oh, new comment. Brittle response, sorry. No. Okay. How do you incorporate modeling of the backfill material reaction with zone joint modeling in hard rock type brittle responses, whereas the fill behaves with high plasticity? Karina or Glenn, would you like to speak to that? I think it's essentially the contrast between the modeling of the brittle rock mass and the softer backfill.
I can make a quick comment. I know Karina may have comments too. The simplest, I mean, there's two types of model we would typically do. If it's a large kind of mine scale model, we would use probably an elastic material for the backfill because we're more concerned with the whole response of the system. But if it's a very detailed model, then you can use some sort of more Coulomb material for the backfill, or even a Subi model so that you can capture the tensile strength of the backfill as well as the the non-linearity of whatever backfill parameters you have. So then you're modeling the backfill, the behavior of the backfill in addition to the material around it so it can deform and fail, if you like, in the stope. Then there's a third level of study where you're going to more detail now. If you want to model the consolidation of the backfill and kind of the non-linearity of the backfill, you could write a fish function to basically deal with that. Or if you've got an air gap in the model, that's the other thing we've occasionally done is have, you can use fish to basically introduce air gaps into the model so that you can have the back of the stope move and then reconsolidate and load. But that's going to another level that requires some scripting. So you can do all that stuff with FLAC3D if it's needed, and it depends on what kind of problem you're trying to solve, really. Did you want to add anything, Karina, or did I miss anything?
No, I think you said everything. Thanks, Glenn.
Thanks, Glenn. I might just add, when you're starting with a stope, obviously, or a tunnel, it's essentially a rock mass material or intact material to start with, but it's possible to essentially also use the null material type. And so what that lets us do is essentially change the rock into a essentially air material, if you will. And of course, you can do that in pieces, depending on the how you're mining and how you're backfilling. And then you can essentially have a zone relax command that, as the model's solving, it gradually essentially reduces the modulus and then resets the stresses periodically in that stope to the point where it's kind of gradually excavated so we don't shock the numerical model. And then because if we've specified the material as we remove it as a null material, FLAC3D or 3DEC, they can track the position of the zones, even though there's technically not any material there. And so when it comes to backfilling that afterwards, we know exactly with the shape of the zones, maybe the walls have converged. And so it's very easy to put backfill back in terms of the workflow of how you might do that. And then in IMAT, Karina mentioned it's possible to include the mining sequence, whether that's tunnels, pit shells, stopes. And then there's a way to essentially specify as part of that series of mining steps based on the geometry of your model to essentially introduce backfill back in after it's been excavated. And you're also able to use a different shape than the original backfill. So if you wanted, as Glenn mentioned, to have sort of, maybe it's not tightly filled, the stope, and you wanted to incorporate a bit of an air gap at the top or slumping of material or something like that, it's possible to do. Okay, another question. How do the zone joints, the opposite faces of the joints, respond to dynamic loading generated in far field and near field? I'm going to follow up with you on that. I'm going to, I'll send you an email sort of as a follow-up. I'm going to have to check with one of our dynamic experts. Thanks for the presentation. Before the simulations, are the numerical models calibrated? If so, in terms of which variables? So I assume you're referring primarily to the Australian presentation. I am not sure for that example that they showed if it was calibrated. Of course, it's always best to have a calibrated model, but numerical models also sort of follow along the feasibility stages. Essentially, as you get more and more information or you're actually operating, you'll have more input, more data to be able to compare the models to. So the types of things that you might look at are, of course, displacements. You could have subsidence on surface that you're trying to match. You could be experiencing issues with, even visually. You've got a pillar mine and certain pillars are failing on you, and you could try to match that sort of behavior. Of course, we can also look at things like microseismicity. IMAT, for example, has a module to import microseismicity and quite a few tools to analyze it. It can also extract simulated microseismicity generated by the FLAC3D numerical model, and then you can compare the two and use that for calibration. Displacement, if you're monitoring sort of changes in the shape or displacements along a main haulage route or in a stope. And then, of course, if you have instrumented cables or some other kind of telemetry, you'd be able to use that. Surface mining, you might have LiDAR or ground radar, tilt meters or prisms. We've recently added the ability to import your tilt meter and prism data recorded on site via IMAT into your FLAC3D model. Then you could compare the model results to those sorts of instrumentation. Jim, would you like to add anything to that?
No, I think that sounds right.
Okay, thanks. Next question. Again, for the Australian example, did you have to import the 147 structures in Rhino Griddle before meshing, or did you mesh without these structures and the zone joints were created entirely in FLAC3D? So, and we've talked primarily about FLAC3D, but a little bit about 3DEC. In 3DEC, we have the ability to take a block and cut it, and basically cut it into smaller blocks and add discontinuities that way. But in FLAC3D, essentially you have to, you can define where the zone joints are, and you kind of have to mesh around them. If it's bedding plane, that's pretty simple. If it's a sort of undulating fault or a series of intersecting faults, then we would generally do that in Rhino griddle. And then essentially we would have a well-connected, watertight surface mesh. And then we would use griddle to do the 3D volume meshing, and it would consider all of those internal faces that would represent the joints. And then griddle also, when it saves the mesh as either a FLAC3D or a 3-deck grid file, it will designate those as internal faces. And so those are things that you can look for by name or group name when you have FLAC3D and you want to convert those and do that separation operation Jim mentioned, and define your zone joints, and then you can start to assign properties to them. IMAT has a similar feature where essentially you import a griddle mesh, FLAC3D griddle mesh. It will look for all the internal faces, and then you can select which of those you want to designate as faults or assign properties to. And then, as Jim showed, you could just type in the properties for one or more of those faults. Next question. Did you run the simulation in small strain mode? Does the choice of small strain, large strain have an impact on how the gap of a joint is calculated when there is tensile failure? I'll speak to the first question, and then I'll ask Jim to speak to the second, if that's okay, Jim. The first one is that in FLAC3D, zone joints are currently small strain only. So I assume that that particular example was modeled in small strain. Sometimes I'd have to double check on that particular model, but you can magnify displacements through the plot items in FLAC3D or 3-deck for that matter. And essentially it will exaggerate the displacement. So that may have been how they displayed those visible gaps. But in general, these are all small strain models. Does that sound right, Jim? Or could they actually separate if you're kind of getting that hinging effect?
Yeah, I mean, I can sort of address the second part here. My guess is that in those plots, they obviously exaggerated the displacement because they would have had to run it in small strain with zone joints. Yeah. The second half of the question is, does it have much effect? Especially in the tensile case? Not really. I mean, if they open up, then the force will become zero on that contact. So whether or not it's large strain or small strain doesn't really matter. The force is still zero. So the only time you would really need large strain is if they were moving far enough that you would be forming new contacts. For example, you had a significant shearing such that, one unit was in contact with the same unit, and then it sheared enough that it came into contact with a different unit, and then the properties might change or something like that. So, unless you have fairly significant shearing, larger than say one zone size, you don't really need large strain. And in these, most of these types of models, small strain is probably fine. Large strain becomes important when you're looking at things like, like you said, Dave, block rotation or buckling or things like that, where you have these large strain type of mechanisms that may be important to the behavior of the system. But I mean, if you're just looking at stability and displacements, it's probably not that important. So.
Great, thanks, Jim. Next question. A more general question regarding meshing. I always thought that one of the advantages of a hexahedral mesh was that it was more stable or reliable when plastic phenomena are of interest. Now I see more and more examples using zone joints, but with tetrahedral meshes, especially when griddle is used. Is this still the case? Do you have recommendations as to the mesh type? Jim?
Yeah, I mean, yes, hexahedral mesh is recommended. The unfortunate reality is that when you put in these very complicated geometries and try to mesh them, it's not always possible to make hexahedral meshes. So what Griddle does is it makes a hexahedral dominant mesh, which means that there will be some tetrahedra in there. And that's just the nature of meshing with these complicated geometries. So, obviously we like it better when there's hexes. Sometimes the tets will sneak in there. Some of our consultants will actually split the tets into hexes. So you turn one tet into 4 hexes. That's certainly possible. It just increases your computation time and so on. But yeah, I guess the answer is yes, we still prefer hexes. Sometimes it's inevitable that you end up with tets.
And Jim, along a fault like that, if it's separating or shearing, is that where most of the displacements you'd expect? So it's not necessarily going to be straining in the zones per se?
It totally depends. I mean, yeah, we know that the tets are not that great when things are going plastic. If you have a situation where all the deformation is on the joint itself and the rock is more or less intact, then yeah, it doesn't really matter. If the rock itself is failing and going plastic, then yeah, it'll probably make some difference. So it totally depends on the problem and what's actually happening. So
fair. Okay, thank you. Next question. To my knowledge, zone joints currently support only small strain conditions. Is there a plan to extend this capability to large strain behavior? So Jim is definitely the right person to address that.
yeah, that's definitely in progress. Extending the behavior to large strain. And I should also mention we're simultaneously working on creating better tetrahedral zones to address the previous question. So at some future date, we'll have large strain zone joints and better tets, and some of these problems will go away. So
great, thank you. Just a couple more questions. Can the loss of resistance of the joints due to stress relaxation, for example, or increase of pore pressure be modeled in FLAC3D? Jim?
Yes, I don't 100% understand the question, but yeah, if you have a joint next to, for example, an excavation, there's going to be some change in the normal stress on the joint. I guess you could call that relaxation. So yeah, then you will see the joint essentially become weaker because you have a lower normal stress, right? Similarly, if you add in pore pressure, you will also decrease the normal stress and the joint will behave as if it is weaker. So I guess the answer to that is yes.
Okay, thank you. I just would note too that with 3-deck or U-deck, you can have fluid flow in the joints and across joints, but in FLAC3D and FLAC2D, we don't currently support fluid flow or pore pressures in the joints themselves.
Yeah, oh no, to be clear, you can have pore pressures in the joints.
Oh, I'm sorry,
It will
yes.
affect the stability of the joints. You just can't have flow along the joints like you can in 3-deck. So
Thanks, Jim. And then the last question. As you mentioned, we can simulate faults with different methods. However, if we include any structure that intersect with fault, such as pipeline, which method would be better? I'm not sure I understand that question. If we include any
I guess
structure,
because I talked about zone joints and ubiquitous joints and interfaces, and the question is if you have some sort of structure intersecting your structure, which do you want to choose? I mean, I guess again it depends on the problem, but unless you really need large strain and you don't have a lot of intersecting joints, it's almost always better to choose zone joints over interfaces. So part one of that question would be use zone joints. Part two of the question would be, should I use ubiquitous joints instead? Again, it depends on, whether or not the mechanism of the joint intersecting the pipeline is important. If you think the offset of the joint at a specific location or a specific joint is going to mess up your pipeline, then yeah, you want to put zone joints in. If you're just looking for a sort of general smeared out behavior, then ubiquitous joints is probably okay. My guess is you probably want the actual joint in there, which would mean use zone joints. So
great. All right, so I'll cut it off there. Thank you again, everybody, for your great questions. We will be posting the webinar to YouTube. And if you're interested, I sent a link in the chat at the beginning of the webinar. If you'd like to meet with us, do what we call a software discovery call. If you have any questions about the software, just click that link. You can set up a calendar appointment. We'd also be very happy to offer a free 2-week trial of any ITASCA software. So use that link and we'll have a chat and we can set you up with that trial as well. Thank you, everyone. Have a good day.